Hello and welcome to McLean 360. In this video, I want to solve some couple of problems with you to illustrate the equilibrium of a rigid body in two dimensions, of course. Let's start with this problem. This is a practical problem of a gardener. Let's read it together and solve it. A gardener uses a 60 Newton wheelbarrow to transport a 250 Newton bag of fertilizer. What force must she exert on each handle? All right, so this is actually a typical application of equilibrium of rigid body. Now, the question we want to ask ourselves is that as this girl is actually lifting this and pushing it, what should be the force that this girl should apply? And don't forget that, since she's holding the wheelbarrow with her two hands, then I'm expecting that there will be some force from the left hand and some force from the right hand. Now, let me do a sketch. I am not going to draw the whole wheelbarrow, but we will just try and do a sketch of the rod which is holding the wheelbarrow. I mean, this rod there, where her hand will be holding this. And what happens is that I have a wheel. Okay, so I have a wheel right here. Now, what happens is that because the wheel is in contact with the ground, there is going to some reaction. There is going to be some reaction force. Let's call it RA from the ground to the wheel. Okay, and there is this 60 Newton, and then there is this 250 Newton. So what we're going to do is that there is a certain distance, which is 0.15, all the way from here. So 0.15 meters. And where the 0.15 is, there we have the 60 Newton force coming downwards right here. And then I have another 250 Newton force. And the line of action is exactly at a distance 250, 0.15 again from the first one. And then finally, there is a distance of um, 0.7 to where her hands are attached. Okay. So now, since she's going to hold it with her two hands, let's assume that each of the hands will do F and F. And she's going to actually lift. Okay. She's going to lift it. And so the direction of the force is going to come upwards in this direction. Then this is going to be 2F, where 2F simply means she's going to use her two hands, right? All right, so at this juncture, what are we going to do? We are actually going to find equilibrium. And for a rigid body to be in equilibrium, there are two equations which we use. Summation of forces should be zero, and then summation of moment should be zero. These two equations are necessary and sufficient for a rigid body to be in equilibrium. All right, now let's look at this. This is what you're going to do. So you are going to sum forces in the y direction. Positive in this direction should be zero. Since I don't have any force in the x, that's why I'm doing forces in the y direction. Now, how is this going to be? So RA is going up, so positive, but 60 Newton is coming down, so negative, right? Then minus this force right here is 250 Newtons. And this 250 Newtons is actually coming down, so it's going to be negated to minus 250 Newtons. And then 2F is going up. Can you see that 2F is going up? So it's going to be plus 2F. So plus 2F. Okay. And this should be equal to 0. In other words, I can say that RA plus 2F should be equal to, that is 60 plus 250. What is that? Let's pick our calculators. What is 60 plus 250? What is it? So if I have 60, if I have 60 and 250, then I'm going to do what? 310. Very good. Let's call this equation 1. And now, I have two unknowns. I have one equation. I cannot solve. I need an extra equation. And this extra equation will come from summation of moments, right? So let's look at summation of moments. So we're going to sum moments about any point at all. But let's take point A over here. Let's take moment about the point A. Since we are taking moment about point A to be 0, then it means RA will not contribute to the moment. And we are going to assume that counterclockwise moment is actually positive. So this is what we're going to do. We're going to start from the 60 Newton force. And you know, the line of action of the 60 Newton force is coming downwards like that. And this moment is actually going to create a clockwise moment about point A. Because if I have this and then 60 Newtons is coming here, clearly it's going to cause it to rotate in the clockwise direction. As a matter of fact, the 250 Newton force is also going to be clockwise. It is only the 2F which is going to go counterclockwise. All right, so let's go together. So 60. So minus, since I'm saying clockwise is counterclockwise is positive. If it is clockwise, I'm going to negate it. And if it is anti-clockwise or counterclockwise, I'm going to make it positive. So 60 into 0.15. Then I'll do another 250. Then I'll multiply this by, you know, the 250 over here. The distance from this point to this point is going to be 0.15 plus 0.15. That's 0.3. So if I do this, I'm going to multiply this by 0.3. And then finally, I'm going to look at the 2F and the distance. You know, this is 0.7 meters, 0.7 meters. Now, over here, we're going to do all the way from here. Then we come to this point, and that is going to be what? So I'm going to do what 0.15 plus 0.15 plus 0.7. And what do I get for that? I'm going to get 1. Oh, man. So the distance is 1. So we don't need to multiply by anything. Yeah, so it's going to be 2F, right? Okay, let me just multiply by 1 so that someone will not be confused. Okay. Now, what happens is that we're going to equate this to 0, right? Because we said that summation of moments should be equal to 0. Now, what can we do with this information right here? If we try to solve for F, we're going to get, let's add this up. So, you know, it's going to be positive right here. So it's going to be 60 multiplied by 0.15 plus 250 multiplied by 0.3. That gives me 84. And what is 84 divided by 2? So 84 divided by 2 is nothing but 42 newtons. So basically, what we are trying to say is that this girl will actually, for this system shown, she would have to apply 42 newtons upward with each hand. So this hand will do 42 newtons, and this hand will also do 42 newtons, and she'll be able to lift up this. Let's look at the next problem. All right, so let's look at the next problem. Let's read this problem together, and then let's solve it. So we are to determine the horizontal and vertical component of the reactions on the beam caused by the pin at B and the rocker at A as shown. We are to neglect the weight of the beam. Okay, so in other words, we should find the reactions at the supports. Over here, we have a rocker, and then over here, we have a pin joint. So how do I do this? I need to draw the free body diagram. Let's draw the free body diagram of this system right here. You know, I have so I have this right here. So that is my beam. And what happens is that, okay, let me bring it here. So I have a beam right here. And then there is this load of 200 newtons coming downwards, 200 newtons. And what else can you see? So that is at point B. Now, at the same point B, I have a pin joint, right? Now, for a pin joint, what happens is that for a pin joint, I've got two reactions, and these reactions are going to be Bx, Bx and By. So there's going to be Bx, and then there's also going to be By. Now, you don't need to really know whether Bx is going down or up, Bx is going to the left or right, or By is going up or down. You just have to give it to any of them. But after solving the question, the values you will get will determine whether BS is actually in the right direction or not. Okay. Now what happens is that at the point D over here, which is 2 meters away from this point, what do you have? You have 100 Newton force coming downwards, vertically downwards. Okay, 100 newtons. Okay, and then at a certain distance, let's say 3 meters away from the 100 Newton force, you have this force right here, which is actually 600 Newton force at an angle of 45. So it means I have to resolve. Resolving this, I'm going to get a force along the y, which is 600 sine 45, and then I'll get a force along the x, which is going to be 600 cosine 45. Let's try to actually reduce this. So 600 cosine 45 is what? So 424.26. Let's write it. 424.26 newtons. And then also I have 424.26 newtons. Now over here, don't forget that there is this force, a rocker at A. And since I have a rocker will give me only one reaction. Okay, only one reaction. So let's call this AY. Only one reaction. That is a rocker for you. So over here, that is the free body diagram that we have. The distance here is 2 meters. And watch this. You can see a certain 0.2 right here. It's very critical to understand that. So if you don't actually know this, you're going to get the question wrong. And this is tricky. He's trying to say that there is a small distance over here, small distance, and that is 0.2 meters. All right, so what are the equations that we're going to use? For a rigid body to be in equilibrium, I need two equations. I need to sum forces to be zero, and then I'll sum moment to be zero. These two equations are necessary and sufficient for a rigid body to be in equilibrium. Now, with the summation of forces, I want to start with the summation of force along the x direction. So we're going to sum forces in the x direction. Every force to my right or whatever, let me use this direction, okay, so that I don't confuse you. Every force in this direction is going to be positive to be zero. So let's look at all the forces along the x. So I have bx. Bx is coming this way, so minus bx. Bx is coming this way, minus bx, and it's going to be opposite to this. So plus 424.26. Is there any other force in the x direction we've not considered? No, to be zero. Therefore, I can say that my bx, which I need, is nothing but 424.26 newtons. Okay, so I've solved for bx. Now let's solve for, let's sum forces along the y. Every force going up should be positive, should be zero. Let's do that quick one. So it's going to be what? AY. Okay, so there's AY here. There is AY here. So it's going to be plus, right? It's going up. So AY. And then what else? So I have 424.26 this time around is coming vertically downwards. So minus. So minus 424.26. And then I have minus 100, right? So minus 100. And then what else? Minus 200, right? So minus 200. And what else? Plus Vy. Okay. So over here, that is the summation of forces along the y. Is there any other force in the y I've not considered? No. Okay. So then let's move on. So how am I going to do this? It's going to be pretty much simple. We got to actually add AY plus BY. And then we are going to add all of this. So minus, let's actually add this one. Okay. So minus 424.26 minus 100 minus 200. What do I get? I'm going to get, okay, let me do it just plus, because when it comes here, it's going to be plus. 424.26 plus 100 plus 200, right? So 424.26 plus 100 plus 200, and this is going to give me that is 74.26. Okay, 724.26. So let's call this some equation 2. So this was equation 1. Now I have two equations. I have two unknowns with one equation I cannot solve. I need another equation, and that equation will come from summation of moments. So if I sum moments counterclockwise is positive about any point, well, I can say that the choice is yours. But let's sum moment about point B, right? Because point B has got bx and by. So let's sum moment about point B. Now let's sum moment about point B equals 0. Let's do that quickly. What do we have? Now, please, I want you to open your eye. Okay, let me do this. First of all, let's look at AY. What is the distance or the moment arm? Notice that AY is all the way from this point to this point. We are taking moment about B. So 2 plus 3 plus 2, that gives us what? So 2 plus 3 plus 2, that's going to give us 7. Yeah. So, but what is it? The moment about AY to this is going to be, so if I have this point and the load is coming this way, indeed, AY is going to cause it to rotate in this direction, which is clockwise, right? So minus 7 AY. And then I'm going to do the same thing for, that is, let's do this for the 424.26. The line of action of the vertical force is in that direction. And in fact, what this means is that I'm going to get a force coming down here, and the distance over here, what is the distance? All the way from this to here. So 3 plus 2, that is 5. But what is it? If I have this 424.26 coming here, it's going to actually make this rotate. And that is what? Counterclockwise. So that one is going to be plus. Is that right? Plus. So 424.26 multiplied by 5. So plus 424.26 multiplied by 5. Is that right? And then I'm going to do this one. But please pay attention over here. Pay attention over here. This force, which is 424.26, which is on line on this one. What happens is that the line of action of this force is in this direction. It's actually on the beam. Okay, let me do it this way. It's actually on the beam. Do you see? Now, what happens is that if I want to take moment about point B, please, it's not 0. There is a small distance over here, and that distance, which is the 0.2, will be acting in that sense. I don't want you to be confused. There is this small distance. We are saying that there is a small distance, which is 0.2, and then our force is coming this way. Okay, so if I resolve this, the 424, okay, so by using the principle of transmissibility, we are saying that the force which is here is actually in this direction over here, 424.26. But there is a small distance, okay? This is the 0.2. In fact, this is tricky. There is this small distance, which is 0.2 here. And this 0.2 is going to be, that is like, this is how what we are saying. We are saying that there is this, so we have this 424.26. However, there is this small distance over here, which is the 0.2. And the moment that is going to cause by this is actually going to cause it to rotate in the clockwise direction. And it's going to be 424.26 multiplied by the 0.2. So minus 424.26 multiplied by 0.2. But many people will get this question wrong. You have to open your eyes and look at it carefully. Finally, I have 100 Newton force, which is at a distance 2. And this is going to cause what? This is going to cause a moment, which is actually That is counterclockwise, right? It's going to be counterclockwise. All right. So positive. So plus 100 multiplied by 2. Okay. Now what happens is that over here, our 200 Newton force over here is coming vertically downwards. So it will pass through B. So therefore it doesn't create any moment. So that is it. I think we are good to go now. Let's equate whatever we have to 0. So I'm going to get minus 7 AY. Then let's do this together. So I have 424.26 multiplied by 5 minus 424.26 multiplied by 0.2 plus 100 multiplied by 2. Okay. And this gives us 2236.48. Okay. So plus 2236.448. Therefore, if I make AY the subject, it's going to be 2236.448. Then I'm going to divide it by 7. What do I get? So if I divide this by 7, then I'll get 319.493. Let's say 319 okay, 0.49. So 319.49. So therefore, it means that AY is 319.49 newtons. So since I know AY, this was supposed to be equation 3. I'll bring AY back into this equation so that I should be able to solve for BY. Therefore, my BY will be nothing but 724.26 minus AY, which is 319.49. And what am I going to get? So 724.26 minus 319.49. What is it? So I'm going to get 404.77. 404.77 newtons. And that is actually my Vy. All right. So I've been able to solve for the reactions at A and then B. So Bx I know, but Bx is the first thing I was able to do. And then I was able to now find By and then Ay. All right. So let's look at the next problem. All right. So let's look at this problem. Now we are saying that there are two links. So I have two links, A, B, and DE are connected by a bell crank, as shown. Knowing that the tension in link AB is 720 newtons, we should determine the tension in link DE as well as the reaction at C. Okay, so what happens is that for a system like this, when we say a bell crank lever, we are saying that this whole thing is actually one body. This whole thing that you see, this BCD is actually a whole body on its own. And then this body can be doing this, it's a whole rigid body on its own, right? And this rigid body is pin jointed at point C. Can you see that? It's pin jointed at point C. Our task is to find the reaction, the tension in DE. So you see the tension in AB. So this is AB. This is the AB he's talking about. The tension in the AB you have been given. But he said we should find the tension in this one. This is the DE. And then find the reaction over here. So how can we solve this problem? All right, let's look at this problem together. Now, please watch this. With this problem, we know, so okay, we know that the tension over here is what? 720 newtons, right? But watch this. What is the tension force? Always the tension force will try and move away from the body. So let's say the tension force is 720 newtons. And the tension force is, you can clearly see that they are saying that this is actually perpendicular, right? This is 90. I see that. But we need to resolve into x and y components. If we don't resolve it, we cannot find the reaction at the supports. So how can I resolve this? It's pretty much simple. Now, let me clean this for now and let me do something. I'll bring it back. So let's watch this. Let's try to resolve this. This distance over here is what? 80 mm. And this distance over here is what? 60 mm. So if this is 60 and this is 80, if I want to find the angle here, pretty much simple, isn't it? Okay, let's say it is theta. Okay, I want to do something. Let's say that the angle here is theta, right? What will be sine theta? So sine theta is going to be okay. From Pythagoras theorem again, this is 60, right? This side is 60, and this side is 80, right? It means that the longer side is going to what? 60 squared plus 80 squared. And that gives us 100. So what it means that this over here is 100 mm, isn't it? And if this is 100 mm, then sine theta is going to be, that is 60 over 100, or the same as 0.6, isn't it? 60 over 100. All right. So that is it. Now we are going to do cos theta, and cos theta is going to be adjacent this side, which is what? 80 over 100. And in fact, this is going to give us 0.8. Okay. So now let's keep it. Okay. Let's keep it like that. But watch this. If the angle here is theta, then I want to resolve this. This is what I will do. Now, please watch this. You see, if the angle is theta, then it means that if I project this onto this, then still this is also going to be theta, right? That is to say, corresponding angles are equal. What happens is that if this side is going to be theta, then we expect that, um, this side, watch this, please. We are saying that this whole angle here is 90, right? However, we can also think about the fact that, let me do it this way so that I get it. This over here is theta, right? And then what happens is that the angle right here, which I need, is going to be what? In fact, this is actually perpendicular to this. We are saying that this is also going to be 90, right? Don't forget that this is 90, this one is 90, right? So this whole thing is also going to be 90. And so if here is theta, then we expect that this portion is going to be 90 minus theta. And if this portion is 90 minus theta, you know what? This and this is also 90, okay? Therefore, if this is 90 minus theta, it means that this small angle here must be what? Theta. This is interesting. So all what we were trying to say is that if this is 90 and then this is theta, then the angle that the tension force will form over here, if I were to draw a vertical, the angle that the tension force will form for the vertical would have been theta. So that's basically what we are saying. All right. So having known this, we can resolve, right? This is 720 newtons, isn't it? And this 720, we are saying it makes an angle theta with the vertical. Okay, having known that, then we are done. Watch this. The tension over here will also move away from the body, and this tension here, let's call it TDE. Okay. All right. Don't forget that there is also a pin joint connection at C. Therefore, I'm going to expect two reactions. Pin joint, two reactions. So CX, and then I will also expect CY. Okay. Now let's do this. We are going to actually sum forces along the x and then equate it to 0, isn't it? So let's resolve the 720 force along the x. So using the fact that the angle is theta with a vertical, then the horizontal side is going to be 720 sine theta, and it's going to come in the direction opposite to the direction we have chosen. And sine theta is 0.6. So it's going to be minus 720 multiplied by 0.6. Okay. And then I have Cx. Now Cx, I have designated Cx to move here. So it's going to be plus Cx. Now there is no force along the x direction again. Therefore, I can say that this is going to be 0. Equating this to this, then I can say that my Cx is nothing but, so what is Cs going to be? Cs is going to be 720 multiplied by 0.6. What do I get for that? 432. So Cx is 432 newtons. That is Cx for you. How about Cy? Okay, so let's sum forces along the y. So summing forces along the y direction for 0, we are going to sum the force over here. You know, in the tension over here, the force is going to come down. Okay, the force is going to come down, and it's going to be cosine theta, but it's going to be coming down, so negative. So it's going to be minus 720, and cosine theta is 0.8. And then, so we are done with that force. And then we have Cy. Cy is coming downwards like that. So minus Cy. And then also our TDE is coming down. So minus TDE. And this is equal to 0. So I can say that, so Cy, so minus Cy minus TDE, or I can also, okay, let me do it this way. Cy plus TDE will be equal to, that is minus, what is this one? 720 multiplied by 0.8. What do you get? 576. So it's going to be minus 576. Let's call this equation 2. So this one was supposed to be equation 1. So I have two equations, two unknowns, one equation. It means that I cannot solve. I need an extra equation, right? And this extra equation is going to come from moment. So let's take moment. Now the interesting fact is that with the moment is going to be pretty much simple. You know, since the tension over here is perpendicular to the crank lever, taking the moment, we will just use the distance all the way from here to here, right? Which was what? 100 mm. And then looking at the line of action, okay, so we are going to take moment about point C so that we can eliminate this. So this force is coming vertically downwards, so we need a distance from here to meet him. And the distance over here is the 0.12 meters. Is that right? So what is going to happen? I'm going to actually, so summation of moment. Summation of moment counterclockwise is positive to be equal to what? 0. Is that right? From here, what we are going to do is that we are going to actually sum moment about C. Okay. Counterclockwise is going to be positive. Now watch this. If I take the moment of the 720 about C, it's going to cause a moment in this direction, which is what? Counterclockwise. Okay. I'm going to cause it in a counterclockwise fashion. Okay. Counterclockwise fashion. And the counterclockwise is positive. So it's going to be 720 multiplied by the distance, which is 0.1. So 720, 100 mm, so 0.1. And then that is 0.1 meters, right? And then over here, This force is here, then this is 0.12. So it's going to be, that is TDE. So this is TDE multiplied by perpendicular distance, which is 0.12. And the moment is going to cause it in this direction. It's going to come, if you follow this, don't follow my hand, right? I'm opposite to you, so don't follow my hand. I'm saying that this, follow what I'm writing here. So it's going to cause it to be clockwise. So it's going to be TDE, so minus TDE multiplied by 0.12. And that is so the 0.12 is this one. Okay, this one here. And so moment should be equal to what? 0. Let's solve for TDE. So solving for TDE, then clearly we can see that TDE will be nothing but 720, 0.1, all divided by 0.12. What is this going to be? So TDE will be, that is 720 multiplied by, what are you getting here? 0.1 divided by 0.12. That is 600 newtons. How about the um, CY? Okay, so having gotten TDE, we can solve for CY from here. So CY is nothing but minus 576 minus TDE. That is going to be minus 576 minus 600. What are you going to get for this? So 576 plus 600, that gives us 1176 newtons. And minus, watch this. So the minus sign is telling us that we assume that CY was coming down, but it's actually wrong. It means that CY is actually should go up. Okay. So at the end of the day, CY is actually 1176. And then you go and correct it over here that the direction was supposed to go up and not down. All right. Sometimes you'll be asked to find the magnitude of C when you have CX and CY. And that is going to be, you are going to take the square root of CX squared plus CY squared, which will give you CX is what? 432. So 432 squared plus 1176 squared. And you are going to get what? The square root of 432 squared plus 1176 squared. That gives us 1252.84. 1252.84 newtons. So that is the magnitude of the reaction at C. Sometimes, if you are interested in the direction, then you can say that theta will be the tan inverse of the component along. Okay, so CY over CX, and the direction will be tan inverse of CY, which is 1176 divided by CX, which is 432. And the theta over here is going to what? So the theta over here is going to be tan inverse of 1176 divided by 432. And that's going to give us what? 69.9 degrees. All right. So this problem has been solved. So thank you very much for watching.